2.3. Okay. 2.3 Properties of Determinants and Cramer's Rule. In this section, we will look at the basic properties of the determinant, and we'll use these results to derive a formula for the inverse of an invertible matrix. So that's probably the most important thing we're going to do, because so far we don't have a formula for A inverse. So if A is any square matrix, for example, if you have A, B, C, D, E, F, G, H, I, we can find the inverse as long as it's invertible by using row reductions. Yeah, by using the inversion algorithm, basically using row operations. But we don't have a formula that will give us A inverse. We have a formula for 2 by 2. So if you have A is A, B, C, D, then we have a formula for A inverse. That's going to be 1 over AD minus BC, which is basically the determinant of A, and then times that by D goes here, A goes here, minus B minus C. So we have this one for a 2 by 2. We don't have a formula for A inverse for a 3 by 3, 4 by 4, 5 by 5. So that's the base, that's the most important thing we're going to do in this section. We're going to develop a formula for the inverse of any square matrix, as long as the inverse exists. So that's the goal. Let's look at these theorems, because we need all of them in order to reach that goal. If A is n by n, then determinant of Ka is k to the power of n determinant of A. So, for example, if you have a matrix that's 3 by 3, like this one, A, B, C, D, E, F, G, H, I, if that is your A, and from this one you create a new matrix Ka, and here you're doing a scalar multiplication, and if you remember, the way a scalar multiplication is done is that you have to multiply every entry here by K. So you get Ka, Kb, Kc, Kd, Ke, Kf, Kg, Kh, Ki. Now the determinant of this matrix, this new matrix, Ka, is going to be k to the power of n determinant of A. And now that I have written it like this, I think it should be clear for you, because you can factor out the k from the first row, you can factor out the k from the second row, you can factor out the k from the third row. So you have k times k times k determinant of A. That's going to be k to the power of 3 determinant of A. So if you have, generally, if you have an n by n matrix, then you will have k factored out from each row. You'll have k to the power of n. So since Ka results from A by multiplying each row of A by k, we can factor out k from each row. That is, we can factor out k exactly n times. So here, if you have Ka and A is this matrix here, you factor out k 3 times, so it's going to be k to the power of 3 determinant of A. You're good? Okay, the next thing that we're going to talk about is what is the relationship between determinant of A plus B and the determinant of A plus determinant of B. Are they equal? And the answer is no. Generally, they're not equal. Generally, determinant of A plus B is not equal determinant of A plus determinant of B. And if you're refuting something, you can just use an example. So, for example, if A is this matrix here and B is this other matrix here, then A plus B is going to be 1 plus 3, 4, 2 plus 1, 3, 2 plus 1, 3, 5 plus 3, 8, That's going to be A plus B. We can calculate the determinant of each one of them. Determinant of A using AD minus BC is a 1. Determinant of B is going to be 9 minus 1, 8. Determinant of A plus B is going to be 4 times 8, 32 minus 9, 23. And you can see that 23 is not equal 1 plus 8. Yeah. So generally, this is not the case. Determinant of A plus B is not equal determinant of A plus determinant of B. Are we good? Now, however, there is an interesting relationship, which I'm going to describe here using these examples. However, if matrices A and B, if they only differ at a single row, if they only differ, so the other rows are the same, if they only differ at a single row, then an interesting relationship exists. So think of this matrix A, it's a 2 by 2 matrix, and this one B, that's also a 2 by 2 matrix, and these two matrices, they have the same first row. So the first row of A and the first row of B are exactly the same. A11, A12, A11, A12. But the second rows are different. The second rows are different. So here we have A21, A22. Here you have B21, B22. Or maybe I can just use letters like this. Let's say A is A, B, C, D, and B is E, F, G, H. No, sorry. The first two are the same. So B is A, B, yes, and then E, F. So that's the situation. The two matrices A and B, they have the same first row, but their second rows are different. So if you look at the determinant of A here, we get AD minus BC. If you look at the determinant of B, and if we add them up, we get AF minus BE, right? So now we can rearrange this. We can write this as AD plus AF minus, if you factor out a negative from these two, BC plus BE. Yes, because we have a minus here and we have a minus here, which can be factored out. And then this can be written as A times D plus F minus B times C plus E. And this is the determinant of this matrix. This is the determinant of this matrix here. If I put A here, B here, C plus E, and D plus F. Because the determinant of this matrix is going to be this times this. So A times A plus F minus this times this, B times C plus E. Okay? So if I have a new matrix that I call C, and this new matrix has the same row as A and B, if it has AB, but the second row is the sum of the second row of A and the second row of B, that's the sum of this and this. So C plus E, D plus F. D plus F. Then I can say that determinant of A plus determinant of B is equal determinant of C. So notice that C is not the sum of A and B. C is the same in terms of the first row is the same as A and B, except for the second row is the sum of the second row of A and the second row of B. So this brings us to this theorem. Let A, B, and C be n by n matrices that differ only in a single row. So all the other rows are the same. One single row, they are different. Say the rth row. And assume that the rth row of C is obtained by adding corresponding entries in the rth row of A and B. Then determinant of C is going to be determinant of A plus determinant of B. And the same result also holds for columns. That is, you can say if A, B, C are n by n matrices that differ only at a single column. Say, for example, the rth column. Then if the rth column of C is the sum of the corresponding columns in A and B, then again, you have this relation. How does this help? So imagine I give you something like this. I ask you to give me the determinant in terms of x, y, and z. So you have x plus 1, y, z, x, y, z, 2, 3, 4. So you know that this is going to be the same as determinant of, so let's say this is our C matrix. And A and B, they have the same second row and third row. I can break the first row into two rows. I can write x, y, z here. And here I can write 1, 0, 0. Because now you agree that this equation holds. This is like having the matrix A. This is like B. And this one here is like C. A, B, C, they differ only at a single row, the first row. And the sum of the first row of A and the first row of B would be the first row of C. So according to this theorem, this relation holds. But the good thing about this is that I know that this determinant is 0. Because generally, if you have a matrix with two rows that are the same, or if you have two rows that are proportional, then the determinant is 0. So the first one is going to be 0. And the second one, I can easily do a cofactor expansion along the first row. It's going to be 1 times the corresponding cofactor. So that's 4y minus 3z. So the answer is 4y minus 3z. Make sense? Any questions? Okay. So we learned that generally determinant of A plus B is not equal determinant of A plus determinant of B. We also looked at one interesting relation in a very special case. Yes, I mean, I'm talking about this theorem here. But generally, determinant of A plus B is not equal determinant of A plus determinant of B. But we're going to prove that determinant of A times B is equal determinant of A times determinant of B. So this is always the case. And it's rather surprising because, you know, calculating determinant is rather complicated. It's a recursive algorithm. Even A times B is complicated operation to do. But still, you get some very simple relation between determinants of A and B and the determinant of the product AB. However, in order to prove this, we need some preliminary results first. So let's take a look at, go back to elementary matrices, and let's quickly review what the determinant of elementary matrices are. If you remember, we said that elementary matrices are matrices that are obtained from I, and I'm going to use I3 as an example. There are matrices that are obtained from I by doing a single row operation. So imagine E1 is a matrix that is obtained from I by doing a row swap. Yes. So for example, let's say E1 represents swapping row 1 and row 2. So E1 would be 0, 1, 0, 1, 0, 0, 0, 0, 1. Yes. Then what would be the determinant of E1? Any ideas? Or a simpler question, what's the determinant of I?
Is the determinant of E1 -1?
Very good. This is 1, and a row swap, we know what the row swap does to the determinant. It negates the determinant. So that's going to be -1. So have these things that I'm telling you in mind. Let's look at E2, which is the result of, let's say, C times row 1. So multiplying a row by a non-zero value, so C is not 0 here, that's also a row operation, and I can perform that, and I get an elementary matrix. So that would be C 0, 0, 0, 1, 0, 0, 0, 1. So what is the determinant of E2 then?
It would be C.
That's right, because you can see that this is a diagonal matrix. 1 times 1 times C is C. And the third type of row operation that we have is adding a multiple of one row to another row. For example, let's say row 2 plus 5 row 1. Then that gives us something like this. 5, 0, 5, 1, 0, 0, 0, 1. So I'm adding 5 times row 1 to row 2. We know that this does not affect the determinant. Yes? So determinant of E3 would be the same as determinant of I. It's going to be 1. You can also see that from the fact that it is a lower triangular matrix, and for a lower triangular matrix, the determinant is the product of the entries on the main diagonal, 1, 1, 1. Okay, so have this thing in mind. You can easily tell what the determinant of an elementary matrix is. If it's the result of a row swap, the determinant is -1. If it's the result of multiplying a row through by a non-zero value C, then the determinant is C. And if it's the result of a pivot operation, then the determinant is 1. Okay, now let's take a look at this theorem. This theorem says if B is an n by n matrix and E is an elementary n by n matrix, then determinant of EB is determinant of E times determinant of B. So we are taking a baby step towards proving this. Yes. Now we are proving it for a special case when E is an elementary matrix. So E is an elementary matrix, B is any matrix. We're going to prove that this is equal determinant of E times determinant of B. Okay, proof. There are 3 cases, and we will consider these cases separately. Case 1. If E results from I by multiplying a row by K, then EB results from B by multiplying the corresponding row by K. Because if you remember, there is a relationship between multiplication and row operations. If you're multiplying any matrix by an elementary matrix on the left, it's as if you're performing a row operation. So for example, if E is resulted from I by, let's say, multiplying the first row by K, and you're doing EB, the new matrix EB is going to be obtained from B by multiplying the first row of B by K, right? So then you can factor out that k out. So the determinant of EB is going to be k times determinant of B. Why is that? Because this is the same as B, except where the first row has been multiplied by k. So you can factor out that k. You have k times determinant of B. However, we just learned that determinant of E in that case would also be k. So I can replace this k with determinant of E. And I have the result for the first type of elementary matrix, case 1. Is that clear? Now, case 2. If E results from I by adding a multiple of one row to another row, then EB would be the new matrix, which is going to be obtained by performing the same row operation on B. However, in that case, we know that determinant of EB would be the same as determinant of B, because doing a pivot operation on B does not change the determinant. So the two determinants are going to be the same. And also, I can say that this is equal determinant of E times determinant of B, because in that case, determinant of E is going to be 1. So 1 times whatever is the same thing. And case 3, if E results from I by swapping two rows, then EB, the new matrix, is going to be obtained from B by swapping the same two rows. So determinant of EB is going to be negative determinant of B, because that's the result of, that's the effect of a row swap. The determinant is going to be negated. On the other hand, determinant of E will also be -1. So this negative here can be replaced with determinant of E, and the result holds for any type of elementary matrix. You're good? Now we can generalize this. If, for example, I have determinant of, let's say, E1, E2, E3 times B, then actually here it's as if I am performing 3 row operations on B. First I perform this one, then I perform this one, then I perform this one. According to the theorem we just proved, this is equal determinant of E1 times determinant of E2, E3B, because this matrix here, you can name it C, and determinant of E1C, if I call that C, I can say determinant of E1C is equal determinant of E1 determinant of C. Then by applying the same theorem again, this is going to be determinant of E1 times determinant of E2 times determinant of E3B. And then if I apply the same theorem again, I get determinant of E1 times determinant of E2 times determinant of E3 times determinant of B. So generally, the expansion or the generalization of the theorem we just learned is what we have here. Is everything clear? Okay, so the next theorem, very important theorem. This one actually adds one statement to those equivalent statements. I'm going to remind you of the equivalent statements. We have 6 of them so far. We say that if A is invertible, then the homogeneous linear system AX equals 0 has the trivial solution only. Then the non-homogeneous linear system AX equals B is always consistent. The non-homogeneous linear system AX equals B has a unique solution. then A is reducible to I. Also, A can be expressed as a product of elementary matrices. I think I mentioned all of them. Anyway, this one actually adds a statement to that. A square matrix A is invertible if and only if determinant of A is not 0. So A is invertible becomes equivalent to determinant of A is not 0. Okay. So let's take a look at the proof. Let R be the reduced row echelon form of the matrix A. So we have a matrix A. We can perform a series of row operations on that. And this will give us the reduced row echelon form of A, which is going to be R. Call it R. Then determinant of R is going to be determinant of this. Which we just learned is determinant of ER all the way to determinant of E1 times determinant of A. Okay, so far, what does this tell us? Since none of these determinants, the determinant of the elementary matrices, since none of them is 0, because if it's the result of a row swap, determinant is going to be -1. If the result of a pivot operation on I, the determinant is going to be 1. And if it's the result of multiplying one row of I by a non-zero number C, then the determinant is going to be that non-zero number C. So none of these are zeros. What does that mean? That means determinant of R would be 0 if and only if determinant of A is 0. That is, if determinant of A is 0, then 0 times whatever is going to be 0. And if this one is 0, then one of these have to be 0. They cannot be the elementary matrices. So it would be determinant of A that is 0. So far, it gives us this. So since the determinant of an elementary matrix cannot be 0, then we have this. Determinant of R is 0 if and only if determinant of A is 0. Now, if A is invertible, then A can be reduced to I. That is, the reduced row echelon form of A is going to be I. Determinant of I is not 0. So if R is I, then determinant of R is not 0, then automatically determinant of A is not 0. So that's one way. If A is invertible, then R would be I, and as a result, because of this, determinant of A would not be 0. Now, the other way, if determinant of A is not 0, then determinant of R is not 0. If R, which is the reduced row echelon form of A, if the determinant of that matrix is not 0, then automatically it does not have a row of zeros. You agree? Because if it has a row of zeros, the determinant would be 0. If it doesn't have a row of zeros, then every row begins with a leading 1. So you have n leading ones. If you have n leading ones in the reduced row echelon form of an n by n matrix, that means you have n leading ones, and in each column you also have a leading 1. That would be I. So then the reduced row echelon form of A is I. That means A is invertible. That would be the other way. So we prove that if A is invertible, then determinant is not 0. And if determinant is not 0, then A is invertible. So here we are using a theorem that we mentioned before. I just mentioned it right now. We had a theorem in 1.4 that says if R is the reduced row echelon form of an n by n matrix, then either R has a row of zeros, or if it doesn't have a row of zeros, then it's automatically I. And the reason for that is that if you have a n by n matrix, you reduce it to reduced row echelon form, and then you don't get any rows of zeros. That means every row has a leading one. And you cannot have more than one leading one per row. You cannot have more than one leading one per column. Then automatically it has to be I, has to be the identity matrix. Okay. Example. This matrix here is singular. How can you tell whether it's singular or not? You can now just take a look at the determinant. Up to now, if you wanted to show that something is singular, you would have to use the inversion algorithm. You would have to write A here, I here, begin doing row operations. And then if at some point you had a row of zeros, then you would say, okay, this is singular now. However, using this theorem, you can tell that this is singular by calculating the determinant. And for this particular matrix, if you study it very carefully, you can see that row 1 and row 3 are proportional. 1 times 2, 2, 2 times 2, 4, 3 times 2, 6. So the determinant of this matrix is going to be 0. And then automatically, it's going to be singular. So this matrix is not invertible because the determinant is 0. Make sense? Okay, so now we are ready for this. Determinant of AB is equal determinant of A times determinant of B. We're going to consider two cases. In case 1, we assume that A is invertible, and in case 2, we assume that A is not invertible. Okay, case 1. If A is singular, that is, if A is not invertible, then automatically AB is also not invertible. Because if you remember, we said that if you have a matrix A that is not invertible and you're using this singular matrix in any product, that product is going to be singular. So if A is singular, then AB would be singular, regardless of B. ABC would be singular. CAD would be singular. So if you have a singular matrix and you're using that matrix in a product, then that product is also going to be singular. So if A is singular, then AB is singular. And then, of course, determinant of A is going to be 0 because we just proved the theorem. Determinant of AB is also going to be 0 because AB is also singular. Thus, this equation automatically holds. 0 equals 0 times whatever. 0 times determinant of B. Doesn't matter what determinant of B is. This is okay. So that's case 1. Any questions about case 1? What if A is not invertible? Sorry, what if A is not what if A is invertible? So singular means not invertible. If A is invertible, then we know that A can be expressed as a product of elementary matrices. That's one of those equivalent statements. The invertibility of A guarantees the possibility of writing it as a product of elementary matrices. So I can write determinant of AB is determinant of this product here, because A can be replaced with a product of elementary matrices. We just learned that for elementary matrices, I can break the determinant into determinant of E1 times determinant of E2 all the way to determinant of ER times determinant of B. However, this part here, I can bring it back to the form E1 to ER. So it's going to be determinant of E1 times E2 all the way to ER times determinant of B. But this here is A, so I get determinant of A times determinant of B. So in both cases, regardless of whether A and B are singular or invertible, determinant of AB is equal determinant of A times determinant of B. Okay, we just proved it, but let's just verify it with an example. Yeah, we are given two matrices, 2 by 2. This is A, this is B, and here we have the product of AB. So if I multiply A, 3, 1, 2, 1, and B, negative 1, 3, 5, 8. If I multiply them, I'm going to get 3 times minus 1 minus 3 plus 5, 2. 3 times 3, 9, 9 plus 8, 17. 2 times negative 1, negative 2, negative 2 plus 5, 3. 2 times 3, 6, 6 plus 8, 14. And then I can calculate the determinant of the product. I can also calculate the determinant of each one of these matrices, A and B, and verify that this is the case. Okay, I'm going to give you 1 minute to do that. You can just use the arrow technique because for 2 by 2, that's the only way you can calculate the determinant, AD minus BC. Check it and see whether that's the case. Okay, so if you do that, you can see that determinant of A is minus 1, determinant of B is 23, and determinant of AB is minus 23, making it making this a statement here true. Any questions? Okay, so next we have an interesting theorem which tells us the determinant of A inverse and how it is related to determinant of A. It's simply going to be determinant 1 over determinant of A. And the proof is very simple. We know that A times A inverse is I. So determinant of A times A inverse would be determinant of I. On the right, we have 1. On the left, we have determinant of A times determinant of B, determinant of A inverse, because we just proved that regardless of what A and B are, determinant of A times B is going to be determinant of A times determinant of B. So if you just divide both sides by determinant of A, yes,
Sir,
this cancels this, you get the answer. Yep.
what does it say next to the second last line? It's determinant of what?
I.
On the right there? I? Okay, thank you.
Yeah. What is A times A inverse? Isn't that I?
Yeah.
Okay. And we know that determinant of I is 1. So that's the proof for this. It's a one-liner proof. Okay. Next, we're going to see what happens if we multiply entries from one row and cofactors from a different row. So for this, I can probably use one of the problems that we had in the test. To make my point. Yeah, this problem. Okay, so this was actually one of the problems in test 1. You have a matrix A. You were supposed to find the minors, and you were supposed to find the cofactors. And so just make sure that everything is all right. Okay. So you know that if I take one of the rows and multiply the entries in that row by the corresponding cofactors, I'm going to get the determinant, right? So for example, if I multiply A11 C11 plus A12 C12 plus A13 C13, I will get the, okay, let me try that again. A11 A C11 plus A12 C12 plus A13 C13. I'm going to get the determinant of A. That's cofactor expansion along the first row. So for example, if I do 4 times 12 plus 5 times 30 plus 8 times negative 26, I will get the determinant. 4 times 12 plus 5 times 30 plus 8 times negative 26. That would be the cofactor expansion along the first row. Or if I expand the cofactor along the first column, that is, if I do A11 C11 plus A21 C21 plus A31 C31, that will also give me the determinant. So if I do 4 times negative 12 plus 4 times negative 25 plus 6 times 7. So if I do 4 times 12 plus 4 times negative 25 plus 6 times 7, that's going to give me the exact same number, which would be the determinant of A. So this is something that we learned before. Now the question is, what happens if I multiply the entries from one row with the cofactors from a different row and add them up? What would happen then? Okay, so what happens if I do something like this? If I take entries from the first row and multiply that by the cofactors from the second row. So A11 times C21, A12 times C22 plus A13 times C 2, 3. So I'm taking entries from the first row, 4, 5, 8, and multiplying them by the cofactors from the second row, negative 25, negative 60, 50. Let's see what happens. 4 times negative 25 plus 5 times negative 60 plus 8 times 50. And let me have a prediction. It's going to be 0. Everybody try this. Let me know whether you get 0 or not.
Yeah, it's 0.
It's 0, right? So here you get minus 100, minus 300, minus 400, plus 400, 0. And this is no accident. If you multiply entries from a row with cofactors from a different row, or entries from one column and cofactors from a different column, you're going to get 0. Let's try that again. So imagine I take entries from the second row, multiply by the cofactors from the third row. So 5, 1, minus 5. I'm going to multiply by the cofactors from the, so these are the entries from the second column, 5, 1, minus 5. And let's multiply them by the cofactors from the third column. So minus 26, 50, and negative 16, and add them up. I will get 0. So I want everybody to try this. Do you get 0? You got 0?
Yep.
Okay, and this happens for any of the possibilities that we have here. If you have one row and use the corresponding cofactors from the same row, you get the determinant. Same for column. If you have elements or entries of one row and you're using cofactors from a different row, or entries from one column and cofactors from a different column, you're gonna get 0. And this is going to help us a lot with finding that formula for A inverse. So if we multiply entries from a certain row or column by the corresponding cofactors and add up the resulting products, we obtain the determinant. What happens if we multiply entries from a row or column by the corresponding cofactors from a different row or column and add up? So as we just saw, the result is going to be 0. So here we have an example. That would be the cofactor of that, and I'm showing the result, but we just checked that with that example from the test. Now, why is this? So we don't have a rigorous proof for that in this course, but we have a special case here which will make it plausible for you why this is the case. So in order to, there's a trick here that we're going to use to prove it for a 3 by 3 matrix. So imagine A is this standard matrix, A11 all the way to A33. And we define the new matrix A prime so that these two matrices, they have the same first row and second row, A11, A12, A13, A21, A22, A23. But the last row of A prime is actually the first row of A prime. So the first row and the last row of A prime are going to be the same. So the last row is A11, A21, A12, A13. And because of the way A prime has been defined, you would agree that the determinant of A prime is 0 because it has two identical rows. Now, the other thing that will happen is that since A and A prime, they have the same first and second rows, then the cofactors for this position, the position 3, 1, from matrix A would be the same as the cofactors for the same position of matrix A prime. Because, for example, cofactor for this position is going to be plus the determinant of the submatrix here. But the submatrices are the same. A12, A13, A22, A23, A12, A13, A22, A23. Because the first two rows are the same. So, and also for the positions, this is the plus position, the minus position, the plus position. I mean, if you think of those plus, minus, plus, minus, plus, minus, plus, minus, plus, for both matrices, it's the same because both of them are 3 by 3. So cofactors are going to be the same for the third row. So since the first two rows of A and A prime are identical, the cofactors from the third row of A and A prime are also the same. Now consider this quantity. A11 times C31. So this entry times the corresponding cofactor plus this entry times the corresponding cofactor plus this entry A13 times the corresponding cofactor. We all agree that this is the determinant of A prime, which is 0. This is the sum of the products of the first from first row entry. At the same time, it's going to be, so we know that it's 0 because it's the determinant of A prime. At the same time, we can think of it as the product of the entries from the first row of A times the cofactors from the third row. So this is the sum of the products from the first row entries and the third row cofactors of the matrix A. So that's one way of looking at it. Yes, that's the entry 1, 1 times the cofactor from the third row. Entry 1, 2 times the cofactor from the third row. Entry 1, 3 times the cofactor from the third row of A. That's one way of looking at it. The other way of looking at it is that it's the determinant of A prime because we are multiplying this entry by the cofactor from the same entry. This entry by the cofactor from the same entry. This entry by the cofactor from the same entry. And we know it's 0. So on the other hand, expansion of the determinant of A prime using the third row, but we know that this determinant is 0. So now it makes it plausible for you that why this happens. If I get entries from the first row and cofactors from a different row, I get 0 because it's as if I am calculating the determinant of a matrix with two identical rows. You good? Okay. So here we have a simple definition, something called an adjoint matrix. You already know what a cofactor matrix is. A cofactor matrix is something like this. That's a cofactor matrix for A. Now, if I just take the matrix of cofactors from A and transpose it, I have a new matrix called the adjoint of A. So whenever you see this expression, adjoint of A, it's just the transpose of the cofactor matrix. So definition, if A is any n by n matrix and Cij is the cofactor of Aij, then this matrix here is called the matrix of cofactors from A, the transpose of this matrix is called the adjoint matrix, and that's how we denote that, ADGA. So, for example, for this problem we have here, if I want to find the adjoint of A, it would be 12, 30, minus 26, negative 25, negative 60, 50, and then the last row becomes the last column, 7, 20, negative 16. Is it clear for everybody what the adjoint matrix is? Okay, now we have this beautiful theorem which gives us the formula for A inverse. For any invertible matrix, A inverse is going to be 1 over determinant of A times the adjoint of A. How do we prove it? We just need to show that if I multiply A and A inverse, I get I. That's what I need to do. I need to prove that if I multiply A and this matrix, I get I, because that's all it takes for this matrix to be the inverse of A. Their product needs to be identity. So let's prove that. If I multiply A and 1 over determinant of A times adjoint of A, I can write this as 1 over determinant of A, because this is a scalar, times A times adjoint of A. Right? So I've expanded it here. 1 over determinant of A. This is an n by n general matrix. And let's say this is the transpose of the cofactor. So A11, A12, A13, all the way to A1n. Then this would be the second row of the matrix of cofactors. C21, C22, C all the way to C2n. And this column here would be the last row of the matrix of cofactors. So now, do you agree that if I multiply these two, I'm going to get a matrix like this? So for example, if it's 4 by 4, I'll get determinant of A, 0, 0, 0, 0, determinant of A, 0, 0, 0, 0, determinant of A, 0, and then 0, 0, 0, determinant of A, if it's 4 by 4. Why is that? Because for any entry on the main diagonal, I am multiplying entries from a certain row by the corresponding cofactors. So entries from the first row times cofactors from the first row. That will give us the determinant. Second row times second column. That would be entries from the second row times corresponding cofactors from the second row. That will give us the determinant. So on the main diagonal, I'm going to get determinant of A, whatever that is. It's going to be a non-zero number. And then off the main diagonal, I am multiplying entries from a certain row and corresponding cofactors from a different row. So for example, for this position, I am multiplying entries from the first row of A and the cofactors from the second row of A. That will give me 0. Then if I do first row of A, cofactors from the third row of A, I get 0. First row of A, cofactors from the fourth row of A, I get 0. So everywhere else I get 0. And isn't this clear? Isn't this clear? That if I multiply these two, I get I. Because if I multiply this by 1 over determinant of A, I'm going to get 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and then finally 0, 0, 0, 1. So now we have a formula for the inverse of any matrix. Is that clear? So using the adjoint method, find the inverse of this matrix here. So I let you do this example at home. I'm going to use the same example that we have here. So imagine I want to use this formula. A inverse is 1 over determinant of A times adjoint of A. I want to use this to find the inverse of this 3 by 3 matrix. So first I need to get the determinant of A. For that, I can use entries from one row and the corresponding cofactors from the same row. For example, if I'm using the first row, I get 4 times 12 plus 5 times 30 plus 8 times negative 26. So that gives me the determinant. Let's do that. 4 times 12 plus 5 times 30, that's plus 150, minus, open brace, 8 times 26, minus 10. So A inverse is going to be 1 over minus 10 times the adjoint matrix, 12, 30, minus 26, minus 25, minus 60, 20. No, wait a minute. 12, 30, minus 26, minus 25, minus 60, 50. And then the last row becomes the last column. 7, 20, minus 60. So I can also write that as negative 1.2, 2.5, negative 0.7, negative 3, negative positive 6, negative 2, 2.6, negative 5, and positive 1.6. So that would be the inverse of this matrix. Are we good?
Yeah.
Okay. So the next thing I want to cover is the Cramer's rule, but I think I should cover that next class. I don't want my lecture to be very long. So I'm going to end the lecture here, and the Cramer's rule remains for next class.